Okay, welcome back to week 2 of Introduction to Robotics, and today we're going to be looking at Chapter 2 of the Ross book, Robot Fundamentals. And the objectives today, we're going to be looking at understanding and defining the parts of a robot, the degrees of freedom, some classifications, configurations, and some terminology. So the robot system, as defined by the Robotic Industries Association, or the RIA, which we discussed last week, but the RIA breaks the robotic system down into two parts, which number one is the robot itself with three major components of the manipulator, the controller, and the power source. And the second part they just kind of classify as the work cell, which could be like the micro computer, PLC devices, HMIs, signal interfaces, all the other peripheral equipment that is needed to make a functioning work cell. FANUC, on the other hand, they add the software as a major component. Okay, so if we look back, we see that the RIA basically defines the manipulator or the robotic arm, and then the controller, and the software actually runs or is found within the controller, and then the power source. So FANUC, they don't really separate the power source, but they have the mechanical unit or the manipulator arm, and then the software, and then the controller, and then all the other peripheral equipment. Alright, so looking at the robotic arm, this is the part of that when people think of robots, this is what we think of is the part that's actually moving. The robotic arm is primary function is to perform specific programmed motions, and it's actually consists of many mechanical links driven by actuators. And actuators, we'll look at that in a little bit, is basically saying we're going to take electrical or pressure energy and convert that into motion. Alright, so the minor components then of the robotic arm are the actuators, which we'll look at in a little bit, and the production tooling. So the production tooling is the part that we're going to add on at the tip of the arm to perform some task. Now the tip of the arm that we're going to attach the production tooling, which could be a gripper or a welding tip, something like that, it's mounted to the moving tip of the robot, which is a flat surface they refer to as the faceplate, sometimes the tool plate, but usually they refer to it as the faceplate. Alright, and so this faceplate, at the faceplate there, we're going to mount the end of arm tooling. Okay, so EOT is an acronym for end of arm tooling. Again, this is like the gripper or spot welder or drill bit or whatever it is that we're going to attach to the robot. It's also known as the end effector or production tooling. Alright, so here's just a picture kind of showing all the different minor components of the robotic arm. So we have the end of arm tooling, we have linkage, we have servo motors, which are going to make the linkage move, and then we have the optical encoders, which are typically mounted onto the servo motor, which tells us what is the position of that servo motor, and therefore what is the position of the faceplate or the end of arm tooling. Okay, the slides are running slow here for some reason. Alright, so here's just a blown up picture of some of the end of arm tooling. We have in the top left corner is a magnetic gripper, and then below that is like a flexible finger gripper. In the middle is a vacuum gripper, and down in the bottom right is a welding tip. Okay. So again, with the robotic arm is moved by actuators. Okay, an actuator is just a term referring to some type of device that's going to change energy into motion. So usually electrical motors, could be hydraulic pressure in there. Now the robotic arm, depending on exactly what kind of robotic arm it is, a lot of them, modern robots have 6 different axes. So these axes are the part that's going to move, and we break those up into 3 different parts. The first 3 axes are group 1, which is the position group, which is moving the end of arm tooling into the area where we need it. And then the second is the orientation. So once we kind of get the tooling where we want it, we also have to kind of rotate it or point it up or down. And so that is done by the last 3 axes, 4, 5, and 6. Alright, so here's a picture of a robotic arm. You can see at the base here at the bottom it's got some bolts. This end of the robot is the part that's mounted, that's not going to move. And so axis 1 is always the axis closest to the mount point of the robot. And so group 1 includes axis 1, 2, and 3, which if you think about like as a human, axis 1 is kind of a waist movement, twisting. Axis 2 is kind of like your shoulder. Axis 3 is kind of like your elbow. And then axes 4, 5, and 6 deal with kind of your wrist movement, and they give you the yaw, pitch, and the roll. So they allow you to point it up and down, angle it sort of left and right as a yaw, and also to rotate it. All right. The controller is what's sometimes thought of as the brains of the robot. That's actually where the CPU is. And so in some ways the controller is just kind of like a PC or a laptop or even a cell phone. It's got a CPU, it's got memory, and it can communicate with other robots or other equipment. All right. The controller then is going to be running software. So we have the application software. So when you purchase the robot, you're going to get this application software. And in a PC, you would probably think of it as Microsoft Windows, the base operating system of the computer. But in industrial robots, they are usually a proprietary type of software that, depending on whether you get a FANUC or an ABB robot or whatever, it's going to perform the same tasks but in slightly different manners. And then the controller, of course, is also going to have the programs that are created by the operators, or at least the programmers who set up the work cell to complete the task. The controller also has memory, just like any other PC. It has dynamic short-term memory, which programs are loaded up into this dynamic memory to be executed. The dynamic memory is also used for temporary calculations or to store inputs from sensors so that it can be used by the program. Then there's the teach pendant. The teach pendant is actually a separate tool, usually connected by a cable, which the programmer uses to, number one, obviously teach the program. But we can also use the teach pendant to jog or move the robot arm manually when we're doing maintenance or when we're trying to teach a program and we need to tell it to go to this point. So we jog the robot to that point and then tell the program remember that point. And of course, all the communication hardware. All right, so the I/O interface allows us to connect up sensors and actuators to the robot. So in a lot of ways, the controller is really like a PLC. If you're aware of PLCs, programmable logic controllers, it's a PC that has lots and lots of inputs and outputs to it. And so the robots, they have the ability to wire up, literally on the large robots could be hundreds of different inputs and outputs to that robot. Okay, so then the teach pendant is sometimes referred to it as a human machine interface or HMI. But the teach pendant here is what allows us slides aren't keeping up with me here. So the teach pendant gives us the HMI, allows us to program the robot, and as I said before, to jog the robot. Jogging is simply meaning we're going to move the arm to a certain position for maintenance or teaching purposes. Okay. So here's just a slide showing some pictures of some different minor components of the controller, the teach pendant, the CPU or the processor, memory, and the I/O interface. Okay, for power sources, and we'll discuss these all in detail later in the semester, but you basically have three different types of power sources. You have electrical, which would be AC or DC motors. These are excellent. They give good speed and very accurate positioning. Hydraulic could be another power source. The advantage of hydraulic is that you can lift very, very heavy loads. And finally, there's pneumatic power sources, which are used quite often for vacuum grippers or finger grippers to activate the gripper. All right, so when we talk about the axes of the robot, these can be either rotational or linear. So the robots we've looked at before, they all had rotational axes, but this particular robot actually has the first axis, which is the one that's mounted to a fixed position that's not going to move, is actually a linear. It just moves back and forth in a linear fashion, and then the rest of the axes are actually rotational. All right. So, but whether your axis of movement is linear or rotational will kind of specify your work envelope. We'll see here in a little bit. So, this is a articulated robot. All 6 axes are rotational. Okay, and when you count the axes, as again, you start counting from the base where it's mounted, and then you count up each axis in numerical order: 1, 2, 3, 4, 5, 6. Okay. So the first 3, as we talked about before, is group 1, which gives us our position, which gets the tool to where we want it in space, and then the last 3 are our orientation. All right, and so when you look at yaw, pitch, and roll, again, it's kind of like we're trying to duplicate human body motion. So axes 4, 5, and 6 deal with the pitch, the yaw, and the roll. Okay. Now the work envelope is the space in which we can get that tool plate to move. So once we attach a tool, then the work envelope of the entire robot with the end of arm tooling will actually be expanded some. But if you think about the tool plate, that tool face plate, which is mounted at the tip of the robot before we mount the tool onto it, okay, the work envelopes basically specifies where we can move and the geometry of the robot. And we'll look at that more next week. But for an articulated robot, the blue area here on this slide shows the movement or the adjustment for this articulated robot. Okay, or where the faceplate, where this robot can get the faceplate to. So anywhere that's white is areas where it can't get to. So you see with an articulated robot, it has a very odd shaped environment there. Okay, the work cell is the area where we're going to put the robot and complete the task. Typically the work cell is going to be closed off for safety to prevent people from moving into the area where the robot may reach. Okay, so another term here is the tool center point. The tool center point is that point in space that we need. That's kind of like your working point in space. So you have the faceplate, which is the tip of the robot, is going to be several inches in size, but if we look at the tool center point is going to be dead center of that faceplate. However, this is with no end of arm tooling attached. And then when we attach the tooling, we need to teach it where that tool center point is at. So we're going to have to define it based on the type of tooling that we're going to attach to the robot. So here in this example we have a welding tip here, and so this welding tip is obviously it's not the center of the faceplate, so we actually have to define that tooling. Okay, so you see the user defined tool center point here. This is done by what we call a tool frame. So the tool frame gives us a frame of reference where the center of that reference is the tool center point. Okay. Now when you have various different types of tooling, you may actually need multiple tool frames. So if you look here, you see this very large gripper it's got vacuum suction cup grippers holding the box up. But it also has these little metal fingers. So these metal fingers are used to like scoop under a bag. So that would be for, say, picking up a bag of salt or a bag of dog food or cat food or something. We can slip these fingers underneath of that flexible bag. And so a gripper like this, then you're going to have at least two tool frames, one for the tool center point when you're using the vacuum gripper, and a different tool center point when you're using the finger grippers. Another thing to be concerned about is the payload. The payload refers to the maximum amount of weight that the robot can lift at the tool center point. Okay, so depending on the type of tool center point, that's going to affect it, but also the type of end of arm tooling or production tooling that we have mounted. So when you look at this, I mean, this gripper in this slide is picking up a box. But when you look at the gripper itself, the gripper, to me, just looking at it, we have no idea what's inside the box, but the gripper itself looks extremely heavy. And so, you have to take in account how heavy your gripper is or your end of arm tooling. And then you also need to build in a safety factor. So you don't want to be operating the robot at its maximum load all the time. So this is a robot here down in the corner. Kind of not showing real well, I guess, because of the webcam there, but this is a 200 IC LR mate robot, which we have two of these in the classroom, and they're rated with a payload of 5 kilograms. Okay. And so they have this payload of 5 kilograms, and that is essentially about 11 pounds, which, they're not a large robot, so they can't lift a whole lot. So remember, though, this 11 pounds or 5 kilograms is at the tool center point. And then we want to always build in a safety factor. Just a rule of thumb one, would be a 20% below the max payload that the robot's rated at. All right, and so if the robot can lift 11 pounds, but we're going to build in a safety factor of 20% or 0.2, then that means that we can lift about 8.8 pounds with this robot safely in a repetitive manner. But and the problem here, example up here, they're telling us that the gripper itself weighs about half a pound. So that means that the objects we're going to be picking up could weigh no more than, say, 8.3 pounds. All right, some other terms we want to consider here are precision. We want to think about the numerical. Precision refers to the numerical value of some value there, and the precision is looking at how many decimal points we're going to take that out. So the more decimal points you take that out, the more precise you can be. Okay, so precision is talking about how many decimal points. All right, and then we have accuracy. So let's say that we wanted to move our tool center point here to the center of these crosshairs. And then the little circles that you see there are where it actually ended up on multiple times returning. So we're telling it to go to a point in space. And we're looking at how accurate we are to that. And then there's another term, repeatability, which says, well, maybe we're not real accurate. So on this slide, we're not actually reaching that tool center point, but we are getting to the we're getting this point here in the top left quadrant, but when we go there multiple times, we're always fairly close to where we were the previous time. If we look at an example here, what we did, we created a program and we wanted it to go in the X direction 23.00 millimeters, and the Y direction 15 millimeters, and in the C direction 6 millimeters. So we run this program, and the first time it went to 23.05, 15.1, and 5.58. So we can then look at the accuracy of this movement right? It was supposed to be at 23, 15, and 6 exactly. And so we see that it was off 0.05 millimeters in the X, 0.1 in the Y, and 0.42 in the Z. So what we want to do is we're going to look at the largest one here. And so we're about 0.42, less than half a millimeter off of where we really wanted it to be. All right, so but now we're going to run this program again and send it back to that same point, and we see that, you know, the accuracy in this case was a little bit better in the X and the Y, but actually worse in the Z. But now that we've got two runs of the program, we can also talk about the repeatability. And so we can see that the repeatability in the X and the Y and in the Z directions, and see the difference between those. So we see that the repeatability was actually 0.45 off in the Z direction here. And then if we run it a third time, we can look and we see that the repeatability in the X direction actually went down, or got worse. That's why it's red there. But so as we run this program multiple times, we can look and see, what was our maximum accuracy from where it should have been, which was that original 23, 15, and 6 millimeters even. And then we can also see what our repeatability of that robot is. Okay, so again, repeatability is how accurate we are within multiple times. Accuracy is how far we are from the actual position we wanted to be, and precision is how many decimal points we take it out to. All right, another term is the resolution. Resolution, when we're talking about measuring, the resolution is the smallest distinguishable increment that we can actually measure. So like on the previous slide where we're talking about half a millimeter or 0.05 millimeters, those are very, very small. It's very hard for the human eye to detect. Okay, another place we talk about the resolution is with the optical encoders on the servo motors. And, the servo motors are rotating around. And they have these encoders on them to detect how much they've rotated. And some of these encoders are just really amazing. And they can detect up to some like 40,000 pulses for one complete revolution of 360 degrees. And so the resolution then is, almost 111 pulses per degree. Or if we look at it in the reverse, we can say 0.009 degrees per pulse. So that means that if you give this servo motor pulse to move at 0.009 degrees, then you can detect that it has moved. And this is, like I say, this to me is very impressive, because with the visual eye, you cannot see that it moved 0.009 degrees. But on the other hand, these encoders can actually detect that. Okay, so that's the resolution. All right, there we go. So we talked about the parts of the robot, the degrees of freedom. We looked at, just briefly discussed the classifications. We'll get into that more next week, and the configurations, and we discussed quite a bit of terminology. So that's it for